Welcome to Lecture 29. This is again Stokes' theorem, but now we're going to do an application in which we make use of a delta function in 3D. The material here is from Reading Assignment 5, Section 4.3. It's a solenoidal geometry with a circumferential current flow. Section 4.6 and additional problems in Section 6. The objectives of this lecture are basically to apply Stokes' theorem for a magnetostatics problem, assuming a Dirac delta function for the source term J, which is the current flux density. Concepts visualization skills are to determine the direction of the field and the functional dependency of the field's magnitude, and to develop the procedure for determining the field given a current flux density flowing in an axial direction in an infinitely long helix. As usual, the second slide is just a summary of the slides to follow, so we'll just skip it. Okay, so this is a magnetostatic, a source-free problem in which we're going to basically make use of the Dirac distribution. And so the field equations, typically as stated in a previous lecture, we can either talk in terms of magnetic field or in terms of magnetic flux density. In both cases, there's a curl of a field and a divergence of a field. In our case, we're going to work with the magnetic field H, and we're just going to give it the label F, and we're going to basically refer to the label J subscript E as just capital J. That's for the current flux density, just to reduce the amount of nomenclature being used. So if we're going to apply Stokes' theorem, which is the case when we're dealing with a source-free type of system, and also we're dealing with a high degree of symmetry, then it'll basically allow us to extract the value of f out of this integral. And Stokes' theorem is going to be applied, which means we take a closed contour integral of the dot product between the field of interest and the tangent vector. And that's equivalent to taking the curl of that vector field and then dot product with the differential area and integrating over the area which is bound by this closed contour here. Now, in our case, the curl of f is known. It's a given. It's J. That's part of the problem statement. And so then it just comes down to doing the calculation on the right-hand side. And again, we're going to try and make use of specific problems in that if we can choose the surface area vector to be in the same direction as J, that makes this calculation that much easier. And don't forget that the surface area is completely an arbitrary degree of freedom, because as long as the surface area that we've chosen is bounded by the same contour, we can basically solve the problem. And so in our case, we're going to choose NDS to be in the same direction of J to facilitate the ease of calculations on the right-hand side. So here's our problem statement. Consider an infinitely long helical filamentary winding with winding pitch A in units of meters. That's basically the distance between turns, so as you wind your way up. And the radius of the helix is capital R. The axis of symmetry of the helical filamentary winding is aligned with the z-axis. The current flux in the filamentary winding is I. That means if you integrate the current flux density over the filament, the value that you get is I, and that would have units of amperes. And so the calculation procedure as before to compute F is as follows. First, determine the nature of the symmetry and determine if you need to use superposition. Secondly, determine the mathematical form of F and establish the shape of the closed contour. So we use symmetry basically to make our choice. Then compute the left-hand side of Stokes' theorem, followed by the right-hand side, and then equate the left-hand side and the right-hand side to compute the vector field F. All right, so let's start with a very simple picture to show how we make our life that much easier. So this is an example of the actual solenoid that we're looking at, and the current is basically flowing around in this direction. Okay, so it's winding its way down. So it appears that the current is actually flowing in an axial direction, but is more or less a current that is a larger component in a circumferential direction, as will be shown on your right-hand side. So using Stokes' theorem, we can basically determine what the direction of the field will be. Not only that, we have two other bits of information of use to us, and that is that the divergence of field will be equal to 0, which means that the field lines have to form closed circles or closed contours. And also the divergence J must be 0, which means the current has to basically return to infinity from infinity. So for instance, any current here at infinity will basically return and eventually end up here. All right, so we use the right-hand rule. So the thumb will point in the direction of J, which will be this way. And just if you take your thumb and follow along the direction of the contour, the fingers will continuously on the inside be pointing in an upward direction. So we know that the field lines on the inside of the helix are pointing upwards, but we know that the divergence of field is 0. So these field lines have to return infinity, form a closed circle, and come back to it. Now, the other thing is a finer point. If you look at a sort of a finite size solenoid, you'll notice that if you're close to the end, these field lines will come around. And if you're very close, there'll be a slight distortion here where they want to come, but then move on to the next one. If you're very, very close, then you form these little closed lines very close to the actual filament. And so this is actually what you would expect to see. If you only focus in this region, you swear basically there's no change taking place. So if you look across here, the field lines are equidistant with respect to each other. That means the field is uniform. Not only that, if you move in this direction, you see no change taking place, which means the field is uniform along this direction. So if we only look at this little segment here, we would say field is uniform this way and field is uniform this way. Now, as you get close to the periphery, then we'd expect that to not to be the case anymore. But because we're considering as an infinite cylinder, then we can immediately see that the F in this region is constant along the Z direction. Out here, it's going to be vanishingly small. So you can almost say the field is 0 out here. And then also you'll notice that there's a periodicity here. So for example, if we look at a halfway point between two windings here and a halfway point between two windings here, that distance, of course, would be the pitch. You'll notice that the pattern repeats itself. So imagine going in this direction and then coming back in this direction. What you see in this direction is negated by anything you see in this direction. And so if we choose a contour which goes this side and then back on this side, where we basically preserve this periodicity, then this will make the contour integration very simple. So these are basically sort of ground rules. This, by the way, comes from an image file you can look at here if you wish. Now, this in itself is too difficult a problem to solve. And so what we'll do is we'll approximate the solenoid as a series of stacked coils, single-turn coils, and the current is more or less flowing exactly in the same direction, which would have been in a counterclockwise direction. And we preserve the pitch between the windings. So this distance is A. So that's a certain number of turns per meter, a certain distance A. So the units here would be A. That's the pitch. And we stack them on top of each other. Now this problem is much easier to work with in the sense that the distance between each of these more or less remains the same on both sides. So this is the approximation to the solenoid. And so this is just a sort of a summary of just what I've stated. So this is our picture that we're going to work with, the one on the right. All right, so the next thing is to establish the symmetry, to shape the closed contour, and to apply the conventions. And so as we discussed in a previous lecture, the criteria for choosing the shape of the closed contour, one of three options. The vector field F is parallel to the tangent vector on a contour segment, and the magnitude of the field F is constant each point on the same contour segment. Hence, F dot T ds is either the magnitude of F ds or minus the magnitude of F ds, and the magnitude of F being constant come outside the integral. Or the vector field F equals 0 on a contour segment, and hence F dot TDS equals 0, or thirdly, the vector field F is perpendicular to the tangent vector T on a contour segment, hence F dot TDS equals 0. So in this particular case, we're dealing with the infinite helical winding. We know that there's a field that's basically in the z-hat direction inside the helix, but it's 0 outside. And so it seems to be that a rectangular contour is the appropriate choice. And there are 4 sides. And so in this particular example, all 3 cases stated above under criteria apply. All right, so the rectangular contour consists of extending a segment beyond the helical winding and make it parallel to the z-axis. And then you have one branch parallel to the z-axis within the helix where the field will not depend on z. We went through that description with the visuals earlier on. And you'll have 2 vertically displaced horizontal branches that extend outward from the z-axis but are located midway between adjacent conductors. The reason why we do this is to basically make use of the periodic symmetry. So for every pitch, you basically repeat the same pattern. And so effectively, this would be the way to set it up. And so if using these 3 conditions basically and a rectangular coordinate, a rectangular contour, we're able to solve the problem. So the conventions, again, applying Stokes' theorem, closed contour integration F dot TDS is equal to a flux calculation, that is the surface integral of the flux density, current flux density, a surface area vector, where the surface basically is the one that's bounded by the contour. So the 2 things, the right-hand rule states that the fingers of the right hand are in the direction of the contour traversal, indicated by TDS. And thus, by default, the thumb points in the direction of the differential area vector ds enclosed by the contour. Usually it is convenient to choose the thumb to point in the direction of j, and thus by default the fingers point in the direction of the vector field f. Okay, so the next step is the solution formulation in Cartesian or cylindrical coordinates. Either one is basically acceptable. This is a question of choice. Now, the difference being that in Cartesian coordinates, the x, y, and z coordinates exist, whereas in a cylindrical coordinate system, we're dealing only with the coordinates r, theta, and z, and r typically cannot be, is a value which is greater than or equal to 0. So in this diagram, we've shown the coil system with z in this direction, y in this direction, whereas here, we're basically only measuring with respect to the axis, the central axis, in a positive sense. So this is r in a positive sense and z in a positive sense. So in this diagram, basically, we've shown that j is out of the page on the left side, into the page on the right side, and that ds is into the page. And why is that? Because if we choose our contour integration to be in a clockwise direction, then according to the right-hand rule, the area would be pointing into the page. Similarly, on this side, the same diagram, the area vector would be pointing into the page. The distance between winding pairs is a. This is called a winding pitch. And the distance between the center of a particular winding and the halfway pit point between 2 adjacent windings is ZA. The contour chosen here is one which is rectangular, and the reason being is that the conditions that we discussed earlier, that FB parallel to T, FB uniform, FB perpendicular to T, or FB equal to 0. In this case, the contributions to the circulation integral due to this contour segment will be 0 because of orthogonality. Similarly here. Outside here, the field is 0, whereas here the field does not depend on the direction z, only to some extent in direction r. Similarly on this side. So these are basically the diagrams that we'll be dealing with in terms of doing our analysis. All right, so let's compute the left-hand side of Stokes' theorem. And because there are 4 contour segments, we basically have each one of these. And again, as I mentioned on the previous slide, F is perpendicular to T2 ds2. F is perpendicular to DF ds4. These are the 2 horizontal segments. And F is parallel to T1 ds1 along the center, along the axis of symmetry. And F is basically, does not depend on Z, so F is uniform. For the TS3D3 segment, which is outside the coil, the F is approximately 0. Z is the vertical height of the contour. So when we look at these 4 terms, only one term survives, and that's this term here, which is along the center, a vertical direction along the center. So what we need to do now is basically determine what T1 ds1 is, and so we're using an explicit representation of the contour. We're just parameterizing as R is 0, 0, Z, and Z runs from ZA to ZA plus capital Z, Z being the length of the contour segment in the vertical direction. T1 ds1 would be just the derivative of this with respect to Z, and so this just becomes 0, 0, 1 dz. And the field is then just F sum of R to be determined, 0, 0, 1, and it's uniform. And so make the substitutions. The area vector basically was the T1 ds1 was 0, 0, 1, and F was in the Z direction. So the dot product of these two gives you 1, and so you're integrating between upper limit and lower limit. This because you F of R times Z. Again, this is fixed for this particular geometry. It doesn't change. So this is just a reminder that Z at A represents the vertical position of the center for the lower winding within the contour with respect to the halfway point between the lower winding and the adjacent winding outside the contour. All right, so now let's look at the right-hand side of Stokes' theorem, which is the computation of the current flux. And so we're going to look at the two options, Cartesian and cylindrical. If we look at a Cartesian coordinate, then the current that basically is flowing through the area, the current that's flowing through the area, which is basically the area which is surrounded by the contour, would have this form. So J in Cartesian would involve a delta function. Y is in this direction, and it's at R, so it's Y minus R. And the Z would be at some location which is offset by A over 2, so this is Z minus A over 2. And the direction of J would be is going to be minus this term. Why? Because it's in this direction, which is minus x hat. In cylindrical coordinates, this would be just R in this direction, Z in this direction, so this would be delta R minus R. Again, this would be Z minus A over 2, but now this is the direction of theta hat. So this would be basically positive for Z hat. I basically is the total current flowing through the filament. In Cartesian coordinates, we would basically consider all of the current density elements that are basically enclosed within the contour. And so this would be a summation from k equals 1 to n, where n is the number of segments enclosed within the contour, and they're just written out in this form. The area vector will be minus x hat dy dz. We mentioned before that the area vector would be pointing into the page, which would be minus x hat. And so for n equals 3, this would be just a sum of 3 elements. We end up with this for the current flux density. For cylindrical coordinates, the difference would be only in the sense that we're dealing now with an area vector, which is theta hat dr dz, and the current flux density is in the direction of theta hat. Again, if you put n equals 3 in here, which is summing over 3 elements, we end up with this expression for current flux density in the event that we decide to model things in terms of cylindrical coordinates. All right, so the next thing is to compute the right-hand side of Stokes' theorem in Cartesian coordinates using the results from the previous slide. So we make the substitution for J and NDS into the expression here. Again, when you integrate over a delta function, it basically produces a 1. And so the integration of this will give you a value of 3 times I. In cylindrical coordinates, effectively, you're doing the same thing. The only difference being now that the area vector is in terms of R and Z, and the direction is theta hat, and the current flux density in terms of theta hat. If you do this computation, you end up with the same answer, which is 3I, which is exactly what you expect to be the case. All right, so the next step is to equate the left-hand side with the right-hand side and finally to compute the field. So either case for Cartesian cylindrical coordinates, we ended up with the left-hand side looking like this and the right-hand side looking like this. And so we want to solve for f of r, and it turns out this becomes 3 times I times 3 over z. Now the numerator on the right-hand side of the equation is the number of turns n enclosed by the contour. Hence, in general, the right-hand side of the equation can be written as follows. F of r is I times n over z. There were 3 in this case, but we could have made the contour higher and enclosed more windings, and this would have been n over z. But this is nothing more than this is nothing more than I divided by A, which is the pitch. In other words, the number of windings per meter, for example. All right, on the basis of this then, and just using this slightly different rearrangement of f of r, we know that the field inside the helix will have a magnitude of I over A, pointing in the z hat direction, and this is more or less true, approximately true, within the helix, which is what we've shown here, and it'll be 0 outside. That's when x squared plus y squared is greater than r squared. Finally, we can graph the magnitude of the field parallel to the z-axis and inside the helix in cylindrical coordinates. So you can see basically its value is constant until you get to the edge, more or less, right? And then basically drops to 0. This being the radius in our example. This example problem, I chose the radius to be 1, current to be 4, and the height of our contour to be equal to 6. And so this is basically the result that we got. All right, so that concludes lecture 29. Thank you for listening.